of it. And when I'm talking about the trig functions of the specials, I'm looking at our 45, 45, 90, and our 30, 60, 90. This is where everything comes in. Okay? This is where all of our special angles build out of. Now, when we wrote these out before, we wrote it out as 1, 1, root 2, 1, 2, and root 3. I know you guys have done that. I know you guys have all seen that. That's not going to be too crazy. When we built our triangles and in the special, or in the unit circle, we switched them from degrees into radian measure. When we did 30 degrees as far as a radian, what do we write that as? Pi over 6. So we knew that at pi over 6, we had a cosine sine value. What was the cosine at pi over 6? And then the sine was 1/2. The next one was at pi over 4. And that one, sine and cosine, or cosine and sine values were the same because your opposite and your adjacent were the same. We wrote it as root 2 over 2. And then the last one was your pi over 3. And those were, what was it? Cosine 1/2 root 3 over 2. Now, do you remember what happened to those values as we rotated throughout the quadrants? What changed?
Sine,
The signs, yeah. So here you are, positive, positive, negative, positive, negative, negative, and positive, negative. And everything just kind of balances itself through that. I know that we've done this. You guys got beat over the head with this last year, so this isn't really anything new. When we start talking about the 6 trig functions at any one of these angles, it's a matter of, can we list out, well, what's the cosine, sine, tangent, secant, cosecant, cotangent of a value. Okay. So as you go into these, if we want to look at a specific example here, if I want to look at like the secant of pi over 4. If I want to do the secant of pi over 4, well, pi over 4 is which angle? 45. Secant is the inverse of which trig function? Cosine. So what's the cosine at pi over 4? You just flip me right. So what happens here if I want to look at the secant of pi over 4, we know that it's the inverse of the cosine of pi over 4. Well, at pi over 4 is a 45. The secant would have been opposite over hypotenuse. Well, I'm sorry, the cosine would have been, sorry, I said this completely backwards. The cosine would be adjacent over hypotenuse. The secant would be a hypotenuse over adjacent. So what's the secant of pi over 4? Root 2. You guys did tons of that last year. Okay, that should not be anything difficult, I hope, right? Hold on. So with those, and oh, I know. Going along with the special right triangles, do you guys remember how to solve for missing side length with the special right triangle? All right, let's look at one. So let's see. Let's say we have a 60 degree and I'm trying to find the opposite to 60 if I know the hypotenuse. Now, what were the ratios of the sides for that? Yeah. What's that? Correct. Root 3, 1, and 2. Now, the way that I've always done this is that I've always set it up kind of like a long form. And you had in Alpha 2 or geometry going way back. You remember we did stuff like this. Across from the 30 was the 1. We called it x. Here was x times the square root of 3, and here was 2x. 2 times something, 1 times something, whatever. There's some scale going on. In that triangle, which one of those sides do we know opposite? The 90. So that means this 90, opposite my 90 is 18, has to relate to this 2x. So 2 times what is 18? 9. That means my value of x, the scale, if you will, the scalar multiplier, is going to be 9. So across from the 30 is 9. Across from the 60 is 9 root 3. That's how we did that long form. But what you were saying it's opposite was 2. You just cut it in half and slap my root 3 next to it. It does the same thing. This is just showing that when we're working with special right triangles, if you want to set it up via one-step algebra problem, it'll work for you. Okay? It's just a different way of writing it out. Vaguely remember that now? Yeah. Okay. And that's the idea. And the same thing goes for when you have it as a 45. If you had it as a 45, and let's say you knew the opposite, the 90 was, I don't know, 8. We knew that the generic pattern for a 45, 45, 90 was x, x, and then the x times the square root of 2. That's where we got that 1, 1 root 2. We know across from what side? The 90 again. So I set up the algebra problem. X root 2 equals 8. Well, it's a one step. How do you undo multiplying by our root 2? And then you just have, remember rationalizing your denominators? Oh. Yeah. And if you remember, there was a nice pattern that happened anytime you had 45, 45, 90, and you had across the 90, cut it in half and slap a root 2 next to it, and it works. Because no matter what, you're always going to be dividing by 2, and you're always going to have a root 2 in the numerator, because root 2 times root 2 is just the 2. That was just a little shortcut. That just meant your opposite sides then would have been 4 root 2. Okay. Do you remember any of your trig identities?
No.
That's what you guys love the most.
The trig identity.
Let's look at the trig identities then real quick.
Mine was 6. Found it.
Oh,
No.
We don't get too crazy on it. Last year we got really crazy on it.
yeah.
Oh. Okay. Last year we got really crazy on these things.
This is your turn, Olivia. Right now.
You know what? I don't remember. I didn't make the sheet because I forgot about that sheet, to be honest with you. So, yeah. So we have our sine. What? It's 1 over cosecant. Cosine. 1 over secant. Tangent. 1 over cotangent. Oh, for those of you guys that didn't have me for trig stuff before, does it matter that I forget to put the theta or an x in there?
No.
Are you okay with that?
Yeah. Why?
Because if you're doing these verify stuff, it's not that big of a deal. That really isn't. It becomes more important when we have to solve equations. Where you see it? And then cosecant is the inverse. It's 1 over sine. Secant, 1 over cosine. And cotangent, 1 over tangent. Tangent, sine over cosine. And therefore cotangent is cosine over sine. The weird ones are the Pythagorean identities. Where you get the sine squared plus cosine squared is 1. 1 plus the tangent squared. Bless you.
Thank you.
Secant squared. And 1 plus cotangent is cosecant squared. And I know last year in honors we spent a ton of time doing a lot of these verify, simplify problems. I mean, we did some really, really nasty ones. Yeah, some of them can be. They really can be. But one thing you guys would be pleasantly surprised about with the pre-calc stuff with this, it doesn't really go into too much detail with it. It really doesn't. You'll see some of the verify stuff today, and then you'll use some of the Pythagorean identities later on to solve some equations. It's really not going to be all that more complicated. Actually, I think it's easier than the material that we did last year in Alpha 2, to be honest with you. What was yours? Okay. So let's do a couple of these and see what we remember. Yeah, I got a big crack of skin, so I just put Neosporin. So what they use these things with in the pre-calc then is to solve other stuff. You're going to do some quick verifies. For example, show that the stuff on the left equals the stuff on the right. Show that tangent times cotangent equals 1. Well, a lot of times when you break them down into smaller, to what they're made of, things just simplify real fast. In this case, what's tangent?
Sine or cosine?
What's cotangent?
Cosine or sine.
So you get sine.
That's 1.
So what happens?
Drop
Those drop, and what do you get?
1.
And you're done. You look very worried.
They're not all that.
Okay.
Yeah, they're definitely not.
Well,
I wish
it's
they were
not
all
like-
like that.
Oh, come on. I mean, I know exactly what you guys are worried about. You're worried about this.
Oh, no.
Oh, no.
No matter
I don't
what
want
they
to
are.
see it yet. Save it for the
Say it doesn't test me, thank you. It's like,
You know what, Mark?
Really?
You signed up for all
You worried about these.
Yep.
yeah,
You're right.
the ugly looking ones.
They don't like when they are called ugly. They have
You're worried about simplifying something like that.
Very
Yeah.
much so.
Okay.
Yeah.
To be honest with you, I haven't seen that many of, or no, really even all that many of them that are that awful. Okay? Seriously, and I'm not lying to you.
It's
Yeah.
just 1.
I mean, it really isn't that the point. Go crazy in here.
There she is.
One of the things that this book will do, I'm not going to go through this one, but one of the things that this book does is that they'll say, find value of how do you write it? Of a cosine theta in cosine, or if sine is 0.6. So they're trying to figure out what's the cosine of some angle if the sine of some angle is 0.6. So what happens here is you start to think about, well, okay, what trig identity can I use that has sines and cosines thrown together that gives me some value that I can use for an equation?
Sine square plus cosine square.
Very good. Thanks. If I use this, that's some equation that has some value. Do you agree? So, you substitute in. Well, 0.6 squared plus cosine of something squared is 1 squared. Since I know that the sine value, basically what I'm doing here is I'm creating some value theta. I don't know what it is, but I know the sine of it, the opposite over hypotenuse, is 0.6. 0.6 and a 1. I'm trying to find out the other part. Because
Right.
oh, did I write this one? Yeah. I was thinking I just did the Pythagorean theorem last hour. I was so used to doing a squared, b squared, c squared. It didn't change it, but yeah, it didn't have to be 1. Okay. I accidentally wrote it as 1 squared just because I did the Pythagorean theorem of geometry last hour and I realized that you don't have to square with 1. So here you get cosine of some angle is going to equal, well, what's 0.6 squared? Well, what's 6 squared? Move the decimal twice. 0.36. Okay with that? Well, what's 100 minus 36?
Wow.
4.
I was gonna say 40 something, and then I just stopped myself.
What's the square root of 64? So what's the square root of 0.64? 0.8. So that means that the cosine value would have to equal 0.8, which means that from that value of theta, the adjacent is then 0.8. You're basically just using Pythagorean theorem to solve for a missing side limit. It's a 6, 8, 10, 3, 4, 5 triangle.
Do you think that we remember those?
I think you do. Okay. And now, if I have this, what's the tangent of theta? Louder, Mr. Murphy?
0.6 over 0.8.
So your tangent of theta works out to be 0.6 over 0.8, whatever that is. And I'm not trying to find the angle or anything yet. We're not doing that. That's when we'll start pressing the inverse buttons on our calculator. Remember how we did that last year and in geometry to find the missing angle? We're just setting up side lengths. Okay, we're just setting up side lengths. We're not going too crazy yet. Question on that at all? Let's see. All right.
Why?
Let theta be acute. A lot of times they put that little part in there that's making theta be acute, therefore you can use the right triangle. Because if theta was not acute, you wouldn't be using the right triangle, would you? And let's say that the tangent Tangent theta is 3. What's the cotangent? And what would be the secant? So this works out to be really straightforward. We're going to draw a right triangle, pick a theta. That's not the right angle, obviously. Tangent would be what over what? Opposite over adjacent. So my opposite of theta has to be how much? And what's my adjacent? What's my hypotenuse? Very good. Square root of 10. 3 squared plus 1 squared. And then could I figure out what the cotangent and secant is then from there? Cotangent would be the inverse of 3. What's the inverse of 3? I believe you're right. The secant is the inverse of what trig function? So if cosine would be adjacent over hypotenuse, what would be the secant? Root 10 over 1, so I just write it as root 10. Okay? You're not worried about finding theta, just write out side lengths, the ratios of sides and stuff. I'm hoping that this is a lot of review, right?
We're getting there. Slowly but surely.
No, and that's why I was going to say, let's just do day 2, 3 together today and be done with this, because I don't think it takes 3 days.
So we're on day 3.
We're on day 2, day 3, yeah.
Oh, I guess this
Well, the day 3 stuff is kind of more of the quick little identities. Just remember what those look like. Now, the problems that are in your book for the identities that I gave you were some very quick verifies. For example, if I look at number 38, number 38 is a question that I had you guys doing tonight. It was show that 1 plus sine times 1 minus sine equals, what do we have to equal? Cosine squared. Show that the stuff on the left equals the stuff on the right. What would you do?
Cry.
Well, after you cry, what would you do? Foil. Good. Back of the book. Look at the back of the book. And this one here, do you guys agree that this is 1 plus something, 1 minus something, so it's a difference of squares?
Yeah.
This is the same pattern as x plus 2, x minus 2. You agree with that? So if I did that and I recognized the pattern, wouldn't that just be 1 minus sine squared? Well, think about Pythagorean identity. Pythagorean identity says sine squared plus cosine squared is 1. So if I move this over, do I get cosine squared is 1 minus sine squared? You're verified. It's those little tricks and those verify steps that you may have forgotten. Okay? When you go back and you think and you shudder of the ideas of how we did a lot of those verify, simplify problems last year in Algebra 2, some of those were just awful. They're not even remotely that difficult now. They really aren't. Don't get me wrong, we'll have a couple of them eventually, but what I have you guys doing today are really like 2 steps, 3 steps max. Okay? Day 2, day 3. Doable. Yeah. Okay? And I'm going to let you guys get started now, and I'll just wander around and help you out. Like I said, this is so much of this unit, this first couple of sections is a lot of review. Go ahead and work on day 2, day 3 now. Yeah. Oh, sorry.
So you said that you got the
Did anybody else need a sheet?
No.
Yeah. Right triangle trig. Used to be okay. The way that Fontana and I were trying to break up the unit themselves is that Sections 3 and 4 are a lot of right triangle traits, identity, stuff like that. 4 and 5 are all the graphing. So we're going to lump everything together. We're going to try and do the right triangle trait stuff first, then we'll do all the graphing stuff. And then 4, 7, 4, 8 is kind of the newer things that you guys are going to look at. 4, 7 was inverse trig functions, and 4, 8 is just some of the applications and models. And that's how we're going to start talking about differences, angles of elevation, depression. We'll start looking at a little bit of bearings, using minutes, seconds, and degrees, minutes, and seconds in the trig values to try to figure out how far apart two ships at sea are. Things that come up in normal conversation.
Yeah, things that definitely.
You never know. Hey, we were watching, we watched with the kids for the first time this weekend, Raiders of the Lost Ark. I love that movie. It's one of my favorite. But Indiana Jones, when he's trying to find the Well of Souls, he was looking through a surveying thing, which is basically a clinometer that you're using to find the angles of the elevation and depression so you can measure distances. It's just a trick.
He would have pulled out his notebook and done a few problems.
He did. He had his notebook and his pencil in his hand. Have you not seen Raiders of the Lost Ark?
No.
Wow. Wow.
I gotta
Harrison Ford.
My kids had the hardest time figuring out that Harrison Ford was, not only was he Han Solo, but Indiana Jones. They're like, wait, Han Solo was somebody else?
Han Solo's in this movie?
Yeah, that's what it was like. Wait, isn't that Han Solo? Where's his Millennium Falcon? He was trying to wrap his head around the fact that it's somebody playing the two things. Like, yes, this guy was like one of the, just a couple of the greatest, fictional characters of all time. It's exciting.
Gotta go.
Yes, ma'am. Yeah, question. What do you got?
I got you.